Good afternoon, everyone. Today, inshallah, we will talk about dynamical systems. This is almost the last lecture of our course. We will have the final lecture next Monday, inshallah. This is one of the very important applications that you are lucky to have this mathematical modeling model with our course. It's a direct application on matrices and it's specific on eigenvalues and the eigenvectors. It will open your scope to plenty of speculations and applications. Okay? Of course, all of our coursework, references, and everything you will find them on Moodle, and the recorded lectures you will find them on YouTube. Now I will go with you step by step by what's meaning of dynamical systems. The idea behind dynamical systems, it's a mathematical modeling for changing for some phenomena that will change over time. Okay? It has plenty of application. I believe the first application that we will go through is the modeling movement between cities and suburbs. It will explain the idea very well. And then I will have a couple of problems, we will solve them together on another models by the end of this lecture. I want you to give a good attention, leave your cell phones and just focus with me. I will start, as I told you, with the city population model, which may change with time compared to suburban population. So if I have a city, a huge city like Cairo or something like this, and we have some suburbans around it, there will be, in most of times, there will be a movement for the population, either from the city to suburbans or vice versa. Okay? This model will focus the light on this issue. We will consider a city with a population of 30,000 and suburban with a population of 10,000. Assume that there are no variation on the total population. On the total population, it will remain the same for a year or something, and we will see, or it will stay the same. Okay, we will see how it's going to affect with time. But there is a migration between the two regions, as I told you just in seconds. Okay, if this is the city, I will have, let's say, we will have a movement from the city to the suburbans by a percentage of 5% of the population. And for the suburbans, this is just 5% of the population from the city will move to suburbans. And let's consider that we have 95% which will move inside the area of the city. And vice versa. Also, we will have certain movement from suburbans into cities. And the 97% of the percent with suburbans will be moving with the same area or the same region. This is actually what was expected to happen from my point of view with the neighborhood here around us. Okay? You have Cairo, it's really very crowded, and now you have the suburbans here for the new administrative capital, and we all were walking to see something like this. Okay, inshallah it will happen in the future. So the mathematical model considers the following. I can consider that the column of x or the vector of x sub t, it represents the population, okay, over time, where x1 of t is the population of the city and the x2 of t is the population of the suburbans. B, the population distribution vector of the year, as I told you, is x1 the population of the city and x2 the population of the suburban. The population movement can be described by the following. I can describe this movement very simply. So I would start, if I want just to play with my, to just draw something very small, I can consider this is the city and that's the suburbans. As you can see from the numbers, this is 0.95. There is a movement 0.05 from the city into suburbans and 0.03 vice versa, where you have 0.97 of the people of the suburbans are moving around. I can write it this manner. I can write x1 at time t, x2 at time t. This is going to equal to For the population of the city, it will consist of 0.95% times x1 plus there is an 0.03 times x2. So you already have your 0.95% living in the city, plus you will have 0.03 coming over from the suburbans. That's the population of the cities. And for the suburbans, you will have first movement of 0.05 from the cities plus the 0.97 of x2. So I can put this movement or this arrangement in the following. You will have x1 of t plus 1, which is the population of the city, and you will have x2 plus t plus 1, which is the suburban, as we explained. Okay, how it's going to be filled? For the city, you have 95% plus the 3% coming to you from the suburbans. And on the other side, these arrows just to show you where the numbers are in our model. And for the suburban, it's going to be 0.05 moving from the cities into suburbans. Here we go, that's the 5%, plus the 0.97, which are really moving with the suburbans in general. Okay, so I can write this into a matrix form, which is very, very simple. And in this we will be connecting what's happening to a linear transform or something like this. So I have the engine, which is our matrix, which is really very simple, 0.95, 0.03. Then you will have 0.05 and 0.97, and those guys are multiplied in x1 of t, x2 of t, and this is x1 of t plus 1 and x2 of t plus 1, which means the increase or the movement will depend on the values that's already exist at the time being, which were 30,000, do you remember? 30,000 and 10,000 for the suburbans. If you multiply them together, you will be able to speculate the number that will appear within the next year. This is why we are putting x1 for the cities the year after this year, which is the amount at this time. And this is also for the suburbans for next year, after 1 year, according to this movement or this percentage of movement. Of course, we can put it, if you remember, as a linear transformation. You have a function times a times a column of variables. Are you with me? So, this is very, very nice to keep in mind. That's this matrix, okay, with the order that we already have. We have A to A, B to A, which they are feeding the amount of the cities. And from A to B, moving into suburbans, and the B to B. This matrix, by this way, I want you to keep it in mind, because if we change the model with a movements like this, we will be benefited from the understanding of this matrix. So I will understand that element 1, 1, it is the feeding of the first company, the first town, the first hotel or something, or the first university, if you're reading, okay, feeding itself. Then you will have the other value, which also a fed for the first source, okay, but from the other company or from the other side or from the suburban as used. Okay, so this is really, really important. Okay, when a mathematical model follows the equation x of t plus 1 equal to axt, these are what I've tried to explain to you. Where A is an n by n matrix, xt and xt plus 1 are two vectors, okay, of Rn, and the t is an integer representing or determining the amount of movements or the amount of objects that you are moving in. In my case, you have t equal to 1 and t equal to 2. Let us show how it is working. The mathematical model is very simple. All you have to do is to insert here the amounts of the population at this year, and you will be able to speculate the risks by the coming year. So if I consider the t is equal to 0 as the current situation, I can speculate what's going to be within the next year, simply by putting 30,000, 10,000 and multiplying. So in a similar manner, or exactly the same, I can find or speculate the population of the city, the population of the suburban within the next year simply. Now I have 30,000 and 10,000. So next year, how it's going to be a hazard? I will insert 30,000 in every x1 of t, which is the multiplication common by matrices. And x2 of t, it will be 10,000. So after 1 year, Ya Omar, the results is going to be 28 and 800 instead of 30. And then this is going to be 11 and 200 instead of 10,000. So that's the movement, and it makes sense, it's logical, because the people who are leaving the city into suburbans increases, it's a 5%. While the people doing the vice versa way, they are just only 30%. So the movement mainly from the city into the suburbans. And this makes sense. Usually people move from the crowded places into the more easier and the more less crowded areas around the center. Okay? Better, as you know, better benefits, better roads, more air, more space, and everything. Okay, I can redo this once more as after the second year. I will take these two values of the population of the first city, or the city and the suburban, and I will make exactly the same with the substitution, inserting x1 of t by 28,800 and putting x2 of t by 11,200, and that's the result for the second year. As you can see, as time moves, the amount of the city decreases, the city population, and the amount of the people who are leaving or getting into suburbans increases. This is for second year. So remark that each year is the input also of the second year. So while we are using this system, you make a first substitution, you will get the elements by first year. If I need to have the second year, I will take the elements or the output of the second year hazard, I will insert them in this matrix, and I will be able to get the amount for the next one. Okay, what is going to be after 20 years or 50 years? And this is something had to be put in design. If you look around you, okay, this is something have to be put in designing all of these places. But as you know, so once you look to this shape, you will discover the following. Look to this color, which is the suburbs, and the other one, which is the cities. So cities will start with 30,000 and will decrease. And on the other side, the suburbans will start with 10,000, and with the years, what's going to happen? It will increase till it reach what's called the steady state. Let's take it. What's the steady state? The steady state, it is a suitable, or the rest, or the constant case, or the movements will be trivial between both of them. Okay? So I will almost reaching a steady state case. Okay, very good. So these are the equations, as I told you. So this process can go for any time, building a table for us if I want to make these substitutions. Each year will develop the next year, but what if we want to know in the future? In this case, we will have to use the system of equations that I told you about. This is the matrix that we already formed, you know how to form it. And now we can find the following remarks. That's an evaluation for the previous results using matrices. So all I have to do is to insert for the first year 30,000 and 10,000. Then I will give the result, which is going to be 28,800 and 11,200. Am I right? Same process, Muhammad. I will try it once more. So I will take the 28,800 and the 11,200 and insert them once more for the second year. Am I right? Okay, so I will get 27,797, 12,304. صح؟ Okay, بص Mr. Hazem, what's happening closely? Look at this case. This is for the second year. I'm talking about the second year. If you look to the second year, you are multiplying the matrix by the elements of the first year. So if I replaced the elements of the first year, which are 28,800 something, by the original matrices, multiplying all of them together, you will discover, Mr. Hazem, that this matrix for the second year will be multiplied in itself in order to get the results for the second year. Do you read me? If I want to get to the third year, I'm going to replace from here, I'm going to replace these values or multiply these values once more in this matrix. And so generalizing this idea, I will come to this form. So for the first year, it's going to equal to A times x0. For the second year, it will be A times x1, where x1 is A x0. So you will end up having a square. So if I'm coming to x3, third year, it's going to be simply A to the power of 3 times x0. And so by generalization, I can come to, for x50, it's going to, after 50 years from now, it is simply A to the power of 50 times x0. So I can get or speculate the situation, the population sizes, after 10 years, 15 years, 20, 50, whatever. Very simple. Now Mr. Omar will ask me, because he is thinking about matrices, that we will face a problem, which is dealing with A to a power. A to the power of 3, A to the power of 4, which means you are multiplying the same matrix and itself 4 times. That's not an easy job to do, okay? But Mr. Muhammad, last lecture, we already knew that there is a technique will help you out in case you multiply the matrix by itself in several times. This is why we will see the eigenvalues and the eigenvectors drawn. So that's the same commitments or the same conclusions that we have. So if we want to know how the situation will be after 50 years, all I have to do is to replace the t by 50, and this how I can get to the distribution that I want. This is the matrix that we want, and we want to take advantage from this relation. If you look, Mr. Hazem, you already told me you saw the previous lecture. The previous lecture was a solution for this case. If I have A to the power of t, I can replace it by B times D to the power of t times B minus 1. What's P, Mr. Muhammad? It is the matrix of eigenvectors. What's the D? It's the diagonalized matrix relative to this matrix. Mr. Ahmed, it seems like you didn't look at the previous lectures. So simply, if I have this matrix, I can replace this matrix by 3 matrices, where if this is to the power of t, the time or the number of repetition will affect on the diagonal matrix only. And this is the diagonal matrix, which means for diagonal matrices, if you have a diagonal matrix and you multiply it in itself, the elements of the principal diagonal will take the power. So instead of multiplying the matrices in each other, I will not be multiplying, just only increasing the multiplicity of the elements of the principal diagonal, which is really very simple and accessible for us. The question is this matrix diagonizable? Can I diagonalize or find a diagonizable matrix with the same relation that I have? This is really very simple. All I have to do is to do the analysis, as I told you, of the eigenvalues and the eigenvectors. So if A is similar to a diagonal matrix, then D will equal to B minus 1 AB, or AK, that's what I was trying to say to you, A to the power of K will be equal to P times diagonal matrix to the power of K, which means the elements of the principal diagonal will take the power, and that's it. Okay, let us remember how to diagonalize matrices. These are some of the propositions which we can use or rely on in order to get a diagonalization of a matrix, or to be able to get an eigenvalue or eigenvector for a matrix. Of course, remember the sum of the eigenvalues of A is equal to the trace. What's the trace? Once more, it is the elements on the principal diagonal, yes. The product of the eigenvalues of A is equal to determinant of A, which is really become handy if you try to find the eigenvalues for this equation too. The geometric multiplicity of each eigenvalue, the geometric multiplicity, it is the dimension of the eigenspace. It is the dimension of the eigenspace as we saw in the previous session. You will have to look at it, okay? And the larger, and each eigenvalue is not larger than its algebraic multiplicity. The algebraic multiplicity means the division of the values of the eigenvalues while we are evaluating them. Also, there is two very nice remarks. If each row of A sums to certain k, so this k is going to be an eigenvalue, and the vector triple ones, or all of these ones, will be one of the eigenvectors. And the four columns, k is going to be an eigenvalue, but it's not certain that you will have those triple ones or those number of ones as an eigenvector. Okay, we already passed through this in the previous session. So what I really want you to keep in mind is that for an n by n matrix, the sum of the eigenvalues of A is equal to trace of A, and also if each column of A sums to k, then k is an eigenvalue of A. These two remarks can work beautifully in evaluating the values of the eigenvalues. Okay, both together. Let's get back to our model. I want to evaluate the eigenvalues with you quickly. Of course, this problem we already solved it previously. Okay, but I will try to go through it with you to just make you remember how to evaluate the eigenvalues and the eigenvectors. I will solve this equation or this matrix by the normal way. Then I will solve it with you using the theories. This is really a revision on the previous session. Come, please, try to do it. Just push it a little bit. Okay, very good. If I want to evaluate simply these values, it's going to be really very simple. All I have to do, as you know, I will have to solve the characteristic equation, which is simply A minus lambda I as a determinant, and it's equal to 0. I will have to solve this equation. If you try to substitute in this equation, it means, Mr. Omar, that we have a determinant where we have 0.95 times lambda, and we have 0.03, 0.05, this is 0.95 minus lambda, and 0.97 minus lambda inside this determinant, and the value is equal to 0. And this is simply going to represent an equation. If you try to evaluate this determinant has how to evaluate it? I will multiply the elements of the principal diagonal, which is going to come up to 0.95 lambda, okay, minus lambda, times 0.97 minus lambda, then minus multiplying 0.03 in 0.05, I believe it's going to come up to 0.15. And then I will try to solve or to expand this quadratic equation, which is going to come up to lambda square. Then you will have minus 0.97 lambda, minus 0.95 lambda, then plus, okay, then plus 0.95 times 0.97 minus 0.15 is equal to 0. And then you will have a quadratic equation. You can solve it by any how, okay? So it's gonna come up to, if you add them together, just to try to do the math using calculator, bring a calculator. Okay, evaluate lambda square minus, rapidly, 0.97 plus 0.95, it's going to come up to? Huh? 0.97 plus 0.95
plus
huh? 1.92.
لحظة دكتور بس
They have the same sign.
0.96
Yeah.
ماشي هقد 0.97 plus 0.95
Yes, that's it. How much is it?
1.92
92. So it's going to come up to 1.92 in lambda. Then multiply 0.95 times 0.97. Multiply them together. Keep it with you for a while. 0.97 times 0.95 minus 0.15 equal
0.7715.
So it's going to equal to positive 0.77. Am I right? Okay. So now I can solve this quadratic equation either using your calculator or the law. If you remember the law will be this: if it is ax squared plus b of x plus c equal to 0, so the law will be x1 and 2 is equal to negative over b positive or negative square root 4b squared minus 4c over 2a. Am I right? This is the law how to get the values of a quadratic equation. Of course, you are right, Mr. Hazen. According to the propositions that we already had previously, I can evaluate the values of lambda away from a quadratic equation. In case if I have a 2 by 2, it's going to be really, really simple. If you remember the propositions, he asked you or he gave you that if you sum the numbers of these matrices by columns and they have the same value, then this value will be one of the eigenvalues of this matrix. So simply, Mr. Hazen, if you get the sum 0.95 plus 0.05, the result will be 1. And if you add 0.23 plus 0.97, the result will be 1. So simply, lambda is equal to 1 is one of the eigenvalues. Also, the sum of the eigenvalues equal the trace of this matrix. So, lambda 1 plus lambda 2 is equal to, adding these numbers to both together, it is going to be 1.92. Am I right? Which means lambda 2 will equal to 0.92. So if you analyze this equation, you will have 1 and 0.92. Okay? If you use the theories that I use now, you will be able to identify that the eigenvalues are simply 1 and 0.92. And they are exactly the same. Now I have what's called an eigenvalues. I will need corresponding to each eigenvalue an eigenvector. How to get the eigenvector? What I have to do is to solve the homogeneous system, which is A minus lambda I in your eigenvector equal to 0. So I will once more making this substitution with each lambda. I will start with lambda 1. Lambda 1 is equal to positive 1. So start substituting, which means you have a system which is 0.95 minus 1. Then you will have 0.03. Okay, am I right? Then you will have 0.05. Then 0.97 minus 1 is equal to 0. The second step, the step after that, you will have a minus over 0.05, 0.03, okay? And then you will have 0.05 and then minus 0.03. If you remark from these numbers, the first row is identical to the second row. So if you add them together, the result simply will be zeros like this. And if I divide the first row in minus 0.05, I will have 1 and 3 over 5 equal to 0, and the sign is negative. Am I right? Which means that my vector should obey this rule. معايا مستر محمد؟ انت طبعا بصيت على المحاضرة اللي فاتت. صح؟ يعني تقدر تكمل، يعني تقدر تقول لهم كده ان ده الفيكتور الاول. This is the first vector, first component. This first vector, second component. Now I have a relation connecting them together, which means u1 sub 1 minus 3 over 5 minus 3 over 5. u1 sub 2 is equal to 0, which means u11 is equal to 3 over 5 u12. So I can say that the first vector consists of two components, u11, u12. I will make a replacement. Yes, Mr. Ahmed, it's an infinite number of solutions for a homogeneous system. So I will replace u11 by the value which is 3 over 5 u12. So it's going to come up to 3 over 5 u12, u12. You are free to use any value of u1 sub 2, any value you choose. Of course, the perfect value here will be putting u1 to 5. If I did this, then the vector, the first vector, is gonna be simply 3 and 5. That's the first vector. Of course, Mr. Omar, you will redo all of these steps once more, but with the value of lambda equal to 0.92. So I'm getting the second vector. That's the second vector, u2, which is corresponding to lambda 0.92. And yes, Mr. Ahmed, once more, it's gonna be 0.95 minus 0.92, which is gonna be 0.03. This value is 0.3. That one is 0.05. Is 0.05. Then 0.97 minus 0.92, I believe it's gonna be 0.03. Are we okay? So, then I will redo the steps as I told you. I will multiply, or as you can see, I can multiply the first row in a -1 and add it on the last row. It will be erased, or it will be eliminated. Okay, and the rank is equal to 1, as you remark. So this is 0, 0, 0, 0. This is gonna be 1 and 1, which means the second vector, first component, the second vector, second component, their addition to each other is gonna equal to 0, which means u2 sub 1 is equal to negative u2 sub 2. So the second vector is simply -1 and 1 after you make your substitution and consider u2 sub 2 is equal to 1. Now I have the two vectors. Now the dream comes true. Instead of dealing with this guy, I can replace it by the matrix, which is simply having the first vector as 3 and 5, and the second vector is, and that's what's called a B matrix. The B matrix will be multiplied by a diagonal matrix. The diagonal matrix, you already know it, with the eigenvalues on the diagonal. So it's going to be 1, am I right? 0.92, those are the two eigenvalues. And then I will multiply by b minus 1 as the example, or as the law, which is going to be 3, -1, 5 and 1 to the power of -1. Of course, I can get an inverse for a 2 by 2 matrix. Do you remember how to get an inverse for a 2 by 2 matrix? Well, it will be like this. 3 times 1 is equal to 3 minus 5, so it's going to be 8. Keep it in your hand. Then I will replace these two elements, am I right? Okay, then I will change the sign of the sides. Then I will divide each element on 8. Okay, you have the inverse. Okay, now I have the inverse of this matrix. Okay, now if I want to speculate back to our main steps of today, this is the A matrix that I can use to speculate the number of population within the coming years. Am I right? So if I have this to the power of k, all I have to do is to put this number to the power of k and that number to the power of k. And multiplying by the population, you will have the result. This is the end of our problem. Let's do all of this once more, step by step. Come on, please now. Okay, on these slides. Okay, easy. Okay, so once more, focus. Okay, so once more, that's the main matrix. عفوا تمام؟ مشكلة؟
بس
Okay, so in general, I will do the same steps. But of course, I have, as I told you, I have two pieces of information. So that's the matrix that we have, 0.95, 0.03. Okay, everything's cool? So, okay, so I have 0.95, 0.03, 0.05, 0.97. Once more, taking advantage of the previous, we remark the following, that if you got the sum of the columns, of the elements of the columns, it's going to be positive 1, it's going to be positive 1, so 1 is one of the eigenvalues. I will get the trace, which is 1.92, so the difference is 0.92. Now I have the two eigenvalues, one of them is positive 1 and the other is 0.92. I will start making the substitution in order to get the eigenvectors. So for lambda equal to 1, I will use the exact same model, but it's going to be 0.95 minus 1, 0.23, 0.3 minus 1. And then I will try to enhance the matrix by the row operations in order to get a reduced echelon form. Now I have the relation connecting the first component and the second component of the first vector. I can put them in a matrix form. Then, using the substitution, moving this guy to the other side, and multiplying or considering V2 is equal to 5, now I have the value, okay, of the first element, which is 3 and 5. In a similar, I believe, in this slide,